Welcome to the AWS Summit Online, and thank you for joining our session today on Designing for Resilience. My name is Raj, a Principal Solution Architect from Amazon Web Services, and here with me is Travis Gallion, our Chief Technologist for ANZ. Together, we have close to 40 years of experience working with many organizations and hyperscalers. And in our experiences, the need to design systems for maximum reliability has really never changed. However, the expectations on reliability has evolved significantly. And our goal today is to give you an approach that you can apply within your organizations to ensure your lives and your customers' lives are not disrupted from bad design choices. All right, let's get into it. So traditionally, customer expectations were somewhat simpler to satisfy. Application architecture was straightforward, usage was very predictable, capacity was planned ahead of time, technologies were more generic, and the tolerance levels for availability was low, but all in all, it was acceptable. Changes to systems was rare, and when needed, it typically required a large change window, with a lot of people hurting, as the impact from the change was never understood entirely. So when things went bad due to changes, the time to recover the system was usually lengthy, manual, and mostly hope for the best. Rollbacks was hard and never really tested thoroughly, and in most of the time it was typically a fixed forward position with a lot of people on deck. However, this did meet expectations, as the experience gap between the failed parts to the happy part was well understood. These expectations are rapidly changing, where less than 100% uptime is no longer acceptable, but also it's very hard to achieve all the time. Speed matters in how an organization can detect, communicate, and respond to reliability issues. This is transforming the traditional system design approaches to a more distributed ecosystem. So what is the new norm? The new norm is for an always-on reliable service that can respond and adapt to changing conditions. And in some cases, the expectation is for a consistent experience, where in others, there is tolerance for a degraded experience. Let me give you an example. A seamless engagement experience across web chat, mobile app, and a call center has a higher expectation for a consistent experience. However, degraded video quality is more acceptable than not having access to video content. This is creating the need for highly distributed and sophisticated system architectures, supported by distributed teams who have multi-dimensional skills, with more rapid but smaller change frequencies to keep up with the new pace of expectations. In fact, let's break down a very simple distributed application, which can actually be complicated. Take, for example, a simple client-server database transaction. There are a lot of steps involved to successfully complete a single round trip. It's actually mind-boggling to consider all the permutations of failures that can happen in this simple distributed system, especially over multiple requests. So imagine how it looks like for thousands or millions of requests. When everything is healthy and working as expected, the end customer has a positive experience. However, when a system has many dependencies, and if one of the downstream components in the chain fails, this has the potential for a direct impact to that experience. If more components fail, this could result in unpredictable experiences for the customer, even to the point of halving the capacity that can be available to service each of the distributed transactions. The traditional way to tackle this challenge has been testing on pressure points for each component, but as distributed systems become more complicated, these test results don't really represent a real scenario. And often, we only change the testing approach after an outage has taken place, which of course is way too late. In my experience, sometimes it's the same offender, it's always DNS. So how do we move into a mode where we are continuously testing, not just for the known scenarios, but also be able to experiment continuously on the unknowns? Here at AWS, one of the tenets for good application architectures is to design for failure. As Amazon CTO Werner Vogel says, everything fails all the time. Resilient applications provide continuous service despite disruption, be it natural disasters, human errors, to hardware failures. Measuring these causes across likelihood and impact helps us to create focus areas. And in my observation, when helping customers who have had a bad day, unintentional human errors has been the most common contributor to a service interruption, typically due to the lack of automation for changes or the failure of the deployment mechanism itself. followed by unexpected load either through an internal system misbehaving or an external threat such as a denial of service attack. Other causes we see are systems not being able to tolerate an interruption to the control plane, but also data center outages, and these things actually happen and have happened in the past. In these scenarios, we encourage you to think deeply about how you design for availability. This is what your customers expect and expecting more of. Other causes that have a rare likelihood but could have a more severe impact include natural disasters such as flooding through to global large-scale events that could interrupt the provider. To mitigate these rare events that carry a greater impact, we encourage you to think about how you should design for disaster recovery and be able to demonstrate this periodically. Treating these two as separate goals ensures you have a much clearer delineation in when to focus on maximum availability versus the path to take to recovery. Combining these two could result in degrading the overall reliability outcome with increased complexity and cost. And of course, as we start to launch more things into space, space jump becomes a reality. But I don't know about you, but for me, zombies keeps me up at night. So we always need to be prepared. So how do you design systems when things fail all the time? To help break this down, we will talk through how you go about design systems when things are inside your control, how you should approach systems when it's outside of your control, and we will cover techniques in managing systems when everything changes all the time. And lastly, how should you be thinking and designing systems that have a much higher degree of criticality? Let's start with architectures where design decisions are inside your control. And we will look to cover the following 6 architecture patterns and discuss what options you have available today on AWS and how this can improve your reliability posture. Traditional enterprise recovery approaches looked at mostly an active-passive pattern, where the passive could be cold, warm, and very rarely hot. So how do you take the good from the traditional and involve these to deliver a simpler and improved reliability outcome? Let's start with a simple 2-tier system with an EC2 instance and an Amazon RDS database within a single availability zone within a single region. As expected, this has many single points of failure. We can improve this system's availability by simply deploying the EC2 instance across more than one availability zone within an auto-scaling group. We front the EC2 instance using an application load balancer with defined health checks that are meaningful. We use Route 53 as a DNS service to connect user requests to the infrastructure, and in the event of an availability zone impairment, the architecture requires no action, as the EC2 instances in the impaired availability zone will start failing health checks, and the application load balancer will do its job. It'll shift traffic away from them. We leverage AWS CloudFormation to automate the deployment of the infrastructure stack, along with monitoring and management tools to support the system. With this simple design, we mitigate many common causes for interruptions. However, not all causes can be mitigated. If an operator error did take place or the deployment pipelines malfunctioned, this has the potential to corrupt the entire system. And this requires a recovery treatment plan to go back to an acceptable state. This would be an agreed recovery point objective or something more familiar, an RPO. A way to design a multi-zonal recovery solution within a single region is to consider the use of one of the availability zones as an isolated or standby deployment. We use AWS Backup Service to create a policy-driven backup plan. We monitor the status of this from an ongoing perspective and have the copy stored in Amazon S3. This will need to take into consideration the recovery point objective. And recovery to this environment can be as simple as a change to DNS, but also can be stood up and tested in parallel of the running production environment. This still does not mitigate all possible causes, and of course, space junks will still be a worry, but more importantly, the zombies are still out there and they still remain a worry. So let's now spend a bit of time in walking through what could be scenarios where there are system components that are outside of your control. So, at Amazon, we build large-scale distributed systems that are composed of independent services where each have a narrow set of responsibilities. This promotes separation of concerns by having well-defined boundaries. As a result, each component can be managed, secured, and scaled independently, and avoids what is commonly known as fate sharing, fail together or not at all. Travis will double-click on this a little bit later on. And one of the highest levels of boundaries we have is the data plane and the control plane. Let's look at the EC2 service. The data plane for an EC2 instance is the daily business of those resources, such as routing packets according to the route tables you define, the reads and writes from storage volumes, and so on. These technical decisions and these interactions sit with the customer's responsibility. The control plane, however, is the machinery involved in making a change to a system, from adding new instances, deleting, or modifying resources. So, if you take the EC2 example in this context, it includes everything that happens when EC2 launches a new instance. The control plane coordinates everything that is needed for the EC2 instance to launch effectively, from finding a physical server for the compute, allocating network interfaces, and many more. But also, it needs to make sure it can propagate all those changes to wherever they need to go. With this in mind, there are scenarios where things are outside of your control that could cause an interruption to your business application. And these scenarios could include an unintentional operator request to the control plane, resulting in a termination or a misconfiguration of the system. The control plane itself fails to complete the intended request. Sudden network burst or routing challenges such as BGP hijacking, or an external dependency that was not understood, or an expectation discrepancy on availability SLAs. Under these situations, the overall impact could be support teams, they experience unknown unknowns, which can lead to unpredictable system behaviors, where applications get corrupted with the data not being able to be restored easily, which results in extended recovery times. This has the potential for now support teams to suddenly enact disaster recovery due to not being able to correlate system behaviors to the actual underlying root cause within a timely manner. So if you've recently undergone a real DR process, you can appreciate that it's not a trivial task. So how do customers do this today, and how do they approach designing for systems that are outside of their control? Customers assume all dependent systems are built to meet expectations and tested thoroughly, and measure this by documented SLAs, which are not engineered SLAs. Customers build redundancy into systems so that if something did fail, they can fail over to an alternate system in the hope it is the same. Runbooks are in place testing for known scenarios. However, not all scenarios can be tested accurately or confidently. Systems are rarely changed, and large changes are perceived safer. And by the time a change is introduced to production, reliability really just becomes a hopeful outcome, being the facade of availability. So, to move towards a more resilient ecosystem, automation is essential. You want to aim for automation everywhere, from making changes to your systems to executing recovery procedures from failures. You want to exercise end-to-end observability and gain insights into key metrics that directly impact the expected reliability and performance goals. Through this, over time, you could anticipate and remediate failures before they actually occur, and then continuously test these scenarios that you know of, but also build mechanisms into how you could experiment with unknown scenarios in a safe way. Because if you're not testing, then you're actually hoping. You want to move to a model where you can also execute changes frequently. This increases your confidence levels for both new changes, but also rolling back if needed in a safe and reliable way. And we are helping our customers by making it easier to put these practices in place. And I believe without stress testing your application, you will not know where it breaks. Chaos engineering as a concept introduces failures in order to find weak spots that would be difficult to find any other way. This is not a new idea. It's been practiced and previously presented by Netflix. However, it's not been available to most customers because of the cost, the complexity, and the knowledge required to implement it. Because we use it so extensively at Amazon and we find incredible value in it, we wanted to make chaos engineering available to everyone. The AWS Fault Injection Simulator is a new service that is available in all of the commercial AWS regions today, except Osaka and the 2 regions in China. This new service will help you to perform controlled experiments on your AWS workloads by injecting faults and letting you see what happens. You will learn how your system reacts to various types of faults, and you will have a better understanding of failure modes. Let me now hand over to Travis, who will talk through what you need to consider if everything in your ecosystem needs to change all the time, including the changes that comes when those zombies start taking over. Over to you, Travis. Good luck.
Thanks, Raj. That was a great overview of how systems can fail in a lot of unexpected ways. Having those really good testing mechanisms is really important, so I'm quite excited to see how things like chaos engineering and fault injection becoming easier to use will change how our customers are looking at their reliability. Speaking of changes, very few big systems these days are static or long-lived. Cloud systems tend to be ephemeral and adaptive, not only because of concepts like DevOps that encourage more and more deployments, but models like elasticity and self-healing can create some implicit behaviors in your architectures, especially when it comes to those unknown unknowns. So when we talk about designing our systems so that a component can fail at any time, one of the most important things to keep in the back of your mind is that when most failures happen when we change something, and when all of our systems are changing all of the time. When I talk about all the time, especially at scale, there are two dimensions that are really important to keep in sync. The first is, of course, simply the velocity of changes themselves. But velocity is something that tends to increase on an exponential scale based on the second dimension, which is the number of components or subsystems that compose your experience. To help put that into perspective, this is a real system graph taken from our Amazon.com web systems. In that architecture, we run more than 20,000 interoperating pipelines, who are constantly in a state of change. On average, a change is happening somewhere in that system about every 11 seconds. That's a lot of volatility. If we didn't create architectures to insulate ourselves from those changes, the inevitable failures that come from things as simple as operator error or as complex as split-brain scenarios would really have a significant impact on the experience that we could deliver to our customers. And I'm pretty sure that our customers don't have any tolerance at all for Amazon having downtime, especially not during the Christmas season or on Prime Day. And speaking of Prime Day, in just that one 24-hour period, the system was processing about 280 million HTTP requests per minute, with DynamoDB peaking at more than 80 million requests per second. And even with those kind of peak volumes, this system actually accelerated its pace of change on that day, thanks to factors like auto-scaling events. So learning to control your changes, especially as you scale, gets to be one of the most important elements of a resilient architecture. Let's take a quick look at how to deal with all those changes. The first thing to make sure is making sure that each change is as small as possible. And when things are starting to change fast, a lot of the time you'll be tempted to batch up your changes into release windows to try to limit their volatility, but that's actually the wrong thing to do. Instead, really focus on making each change as atomic as possible so that you can audit and measure its impact, and really focus on your ability to contain the blast radius if something does go wrong. And inevitably, something will go wrong. The other thing that will really help you here is a strong focus on automation. When you're operating your systems with techniques like pipeline deployments, then you have a clear change vector, at least with those known changes, which helps you to isolate failures and contain them as they happen, so the health of the overall system is maintained. Circuit breakers and throttling can be really useful here, so focus on those concepts like exponential backoff or graceful degradation, which can help you speed up in controlled ways. We'll take a deeper dive now into a couple of these techniques that I think are particularly important: bounded context and fractional deployments. And then we're going to have a quick discussion about cellular architectures, which is where I think we'll all be heading pretty soon. Okay. The first important concept that needs a bit of exploration is hopefully dispelling a myth that we've had in the technology industry for a long time. The myth is that maximizing redundancy is really the key to making a resilient architecture. No doubt, redundancy is very important. Obviously, if you have a component failure, like in a disk drive or network partition, then having a second copy there is critical. But when things start changing at pace, more of your real failures will be the impacts, those side effects, which are most often caused by a dependency somewhere between your components. In this case, the introduction of redundancy actually tends to decrease the total reliability of your system. This is because the failure of any node in the system will cause the entire system to fail. Alternatively, if you think about the same system in a loosely coupled way, then the introduction of redundancy tends to increase your overall availability. Modern cloud systems are easier to make redundant through the use of context boundaries, like multiple availability zones. So in this case, focusing your architecture attention on loose coupling between layers and bounded context will give you the biggest bang for your buck. When you have a loosely coupled system, meaning that you have clear API isolation and really strong blast radius partitioning between components, And of course, those components on the data plane need to be statically stable with respect to their shared control planes, including those AWS control planes that they interact with. Then you'll compound your total availability. And that's how you increase your aggregate uptime of your systems and make sure your customers don't experience those bad days nearly as often as they otherwise would. The second really important concept that you should probably be considering at this point is thinking through how to control your blast radius with respect to the changes themselves. Meaning, how do you limit the impact to being as small as possible? The best way to think about that is through concepts like release engineering, things like fractional deployments. These are techniques like blue-green deployments, or concepts like using canaries to make changes which gradually roll out to more nodes as stability is observed. Just don't forget to put in a little bake time between your deployments. It sometimes takes quite a while, or more load, before your systems will exhibit any kind of failure. Also, don't be afraid to roll back before you hit that tipping point. It's much better to have a fractional failure than to have a whole subsystem fail. Be particularly careful with stateful changes that can't be sharded or partitioned, as those tend to be one-way doors that are much more challenging to recover from. Okay, we've talked about managing your bounded context and a little bit about release engineering. So what happens when you put those concepts together? Where I think most architectures is moving is toward more of what we call cellular architectures. What that means is that an entire subsystem, with all of its moving parts, is considered a cell. I like to think of this a little bit like an M&M, a hard candy shell with a soft gooey center. And when you think about redundancy, it's less about the individual components, like a cluster or distributed disk, but more about the cell as a whole, which carries the redundancy. In this case, you want to be really sure to have strong bulkheads between cells, and make sure that you want to treat those boundaries with strong encapsulation. You have to be really strict to make sure that nothing can interact with your cells except through the front door. Of course, even with cells, you still want to practice all the good blast radius mitigations like shuffle sharding and traffic shaping to help contain your cell. One thing that some customers can be confused about is the relationship between cells and availability zones. How does that work? Well, how it works is that AZs provide your system with redundancy. And by that I mean that they're physically separated from each other and maintain very low latency connectivity that allows them to do things like create active-active quorum between them. Cells, on the other hand, are a way to achieve compartmentalization, meaning that you have logical copies of your stack that are isolated from each other while also using AZs for physical isolation. In this way, you can essentially compound your blast radius containments, which really does have a very strong impact on your overall reliability. So what does that all mean in practice? Well, let's take a look at the same architecture that Raj was looking at earlier. In this case, we have some EC2 instances and an Aurora database. So let's take a copy of all those pieces. Once we have two copies, we isolate them as cells and hide their internals from the system, usually by providing an API around them. The last part is creating a capability to route between and to individual cells. In cellular architecture, this is usually called the thinnest possible router. Let's take a deeper look at how that works. These routing layers have to be extremely reliable, very, very stable, so we give them a bit of special attention. First off, they need to be horizontally distributed, typically in quorum using something like Paxos or Raft. And of course, they really need to be statically stable with no externalized state, no disks that can fail, and definitely no databases allowed. This means that their configs need to be kept very, very simple. And remember when I said that everything changes all the time? Well, this is actually the exception to that rule. These parts of the system change very, very infrequently, which adds to their overall stability. As a rule, we tend to change these things less than once per month, which is pretty slow when you think about changes happening in a system every 11 seconds. Okay, we're almost done. I hope that gave you a few ideas for how you can stay resilient when things are changing all the time. But sometimes there are systems, or more often as we saw in our cellular architectures, parts of a system, which require an extreme amount of reliability. These tend to be quite rare, but the good news is that the cloud is a really great place for dealing with those kind of problems as well. So let's have a quick chat about what we do for these extreme reliability. First off, let me try to explain what I mean by extreme reliability. These are systems like hospitals, or even military systems, where failure has a really big impact, such as the loss of human life, or big banking systems, where a bad day would mean challenges to economic stability. We also sometimes mean things that are systems which are just too big to fail. Like when Netflix was streaming Game of Thrones, the world had high expectations and just wasn't going to put up with any failure. Well, at least not a failure on the technology side. I'm not going to make any judgments about the failures of the plot for that final season. On the technology side, we tend to look for things like 5 nines of uptime, which is very different than an SLA. I mean real uptime here, not that stuff the lawyers talk about. And any RPO that is less than 5 seconds, which accounts for things like speed of light in a real-world scenario with buffer sizes larger than a few bytes. Okay, so what do we do about these type of systems? At this point, you can start thinking about taking advantage of multiple AWS regions. There are a number of ways to communicate between regions, and some really cool services such as Aurora Global Databases and S3 cross-region replication that make this a lot easier for you to handle. But the caveat is that you'll always have to manage the latency that comes from the distance, and that latency can be significantly higher than the latency between availability zones. So for instance, you can opt to have a single write region with an eventually consistent read region, which is a great way to think about delivering a seamless distributed experience if you don't have to worry too much about strict consistency. So make sure that you pull out your old CAP theorem textbooks when you want to start looking at these kind of active-active configurations. In my experience, these tend to work best when you can effectively shard traffic between regions, which is what many of our largest customers do. For most customers, though, quite a bit of complexity is introduced when you add redundancy with those increased latencies. So should you be thinking about mitigating that complexity? For a lot of multi-region customers, we found that the focus for many failure scenarios is less on maintaining total availability and more on reducing the downtime and impact of recoverability into a secondary location. There are different techniques for doing this, all the way from pilot lights to hot standbys, which can have some significant cost implications. Don't forget about those big data transfer costs. But for many extreme reliability systems, reducing RTO, and in particular RPO, can have a significant impact on your customer's overall experience. For instance, systems like global payments providers need the smallest possible downtime with minimal impact to data loss as possible, so they tend to optimize around multiple AWS regions this way. So what does that mean? These types of architectures are great for mitigating things like full region failure, including things that we all tend to worry about, like floods, earthquakes, or a nuclear war. Personally, if there was ever really a nuclear war, I'm thinking we're all going to have bigger problems than making sure we can check the bank balance online. There's still not much you can do around internet failure. And of course, all those dinosaur-killing meteors coming back, or Raj's zombies, as far as I know, we still don't have any good answers for that one. AWS continues to deploy more and more infrastructure around the world, and significantly in this part of the world, which means that you'll be able to take advantage of more sophisticated architectures, and that hopefully will give you the confidence to think about deeply crafting those ultra-resilient systems that our customers keep expecting. I have no doubt that their expectations are going to keep getting higher and higher. Here in Australia, we're even more excited to have our second domestic region planned to launch in Melbourne in 2022. I'm really so excited to see how our Aussie and Kiwi customers are going to push the envelope on all those multi-region capabilities. Okay, so what have we talked about so far? Well, we looked at traditional recovery models. This is where most organizations are focused on when they're building on-premises architectures. We spent some time thinking about what happens when zombies attack our data centers, so we have multi-zonal options for resiliency and recovery between them. For those systems that need it, we talked about using multiple AWS regions to create an even stronger story around mitigating things like natural disasters. And finally, we talked about how to combine these techniques to create things like cellular architectures, which can achieve the highest levels of reliability. For instance, our S3 system focuses on its durability and can achieve 11 nines. So that's the kind of bar we'll have to be thinking about pretty soon. Okay, that's definitely a lot to remember. So here are the things I want you to take away, hopefully, from here. First, please remember to focus on your testing. And wherever you can, make sure you're not just testing for the known scenarios, but also those unknown unknowns. Do try to understand your blast radius. Control your bounded context and your dependencies to maximize the value of your redundancy. In that same vein, make sure that you're thinking about different types of changes. Not all changes are equal or binary, so give yourself flexibility whenever you can. Be selective when you approach extreme reliability. Balance the engineering with practical trade-offs, but feel confident that it's there when you need it. Lastly, start by making sure that you're taking full advantage of spanning availability zones before you also jump into multi-region or into cells. If you're looking for some more information to study at home, here are also some great resources that I would recommend having a look at. There are some links here from the well-architected papers and also a great lab. I've also included a link to Adrian's blog post. He's really passionate about his chaos engineering, and it's a great read. Thank you for spending some time with us today, And please do reach out to us if you need any help with your reliability journey. If you're also looking for some more formal training, please do visit us at aws.com/training. Thank you for listening and learning. Before you go and enjoy the rest of the summit, please do remember to submit your feedback form. And thank you again.